There we go. Welcome, everyone. I'll just quickly introduce myself and also Mark. If you're not familiar with TechUcon, for those of you who are familiar, bear with me. But yes, we are a nonprofit industry association based up in Whitehorse, and we support the tech community up in the north. We run a bunch of events like this. And generally, we try to help both business owners, but also people who are tech curious, understand technology on a deeper level so that they can see how they can apply it both in life and in their business as well. Today we have Mark Jackson joining us from Quantinum. Mark, maybe I'll let you introduce yourself and the company because I don't want to make the mistake of butchering it. So I'll let you take it away from here, and then you can dive into the presentation.
Great. Thank you so much, Chin, for the invitation. It's a pleasure to be here. I hope next time I'm there in person. I would love to come up there. So my name is Dr. Mark Jackson. I'm the senior quantum evangelist at Quantinuum. My personal background is in physics. For most of my life, I did something called string theory and cosmology. And then 8 years ago, I joined a small startup doing quantum computing. We're now a very large company. Um, so the company is called Quantinuum, and we were the merger between Honeywell Quantum Solutions, which focused on quantum hardware, and Cambridge Quantum Computing, which focused on quantum software. And so today I'm gonna be telling you about what is quantum computing, and I'm not assuming that you know anything at all about it, because most people I talk to actually don't know very much about it. And so if you don't really know what it is, that's perfectly fine. And if you do know what quantum computing is, that's okay too, because I'll talk about some of the latest developments and some of the applications that people have been focusing on. So I think there's a little of something for everyone. Um, Let me begin sharing my slides here. And and I think you should be able to see that there, I
Yeah,
think.
looks good.
Um, Good. So let me start. So in this one slide, I want to talk about what is quantum computing, and I'm going to talk about two different things. There's 2 points here. If you can remember these 2 points, you are ahead of 95% of the people that I speak with, because there's a lot of misunderstanding about what it is and what it's not. And so if you remember nothing else from my presentation, just remember this slide. So the first thing I would like you to remember is that quantum computing is not just a different type of, sorry, it is a different type of computer. It's not just faster, because that's a very big misconception. And to put this in perspective, imagine this is your laptop. So you kind of know what it is, you're very familiar with it. And I've sometimes heard people say that quantum computing is like a supercomputer. That is not really true. A supercomputer would be like this. A supercomputer is the same as your laptop, it's just more of it. But fundamentally, it's exactly the same type of computer. A quantum computer is more like this. It's built completely different use, structure, everything. And so that's the first thing I would like to get across. The second thing is quantum is not just fantasy. It's absolutely reality. It's already being used by many people. There's many groups building them, and we're starting to get quite good at them. And just to give you kind of an illustration of some of the numbers, there are hundreds of thousands of users on IBM's public machine. And then for our own compiler, which we call Ticket, we've had over 2 million downloads. And so many people are already starting to use quantum computing. And so if your business, your industry is not already thinking about this, you're already behind. And so I would encourage you to start thinking about how quantum can help your business. The past year has been amazing. These are just some of the headlines of the past year. So you probably saw that Google has made some announcements. They made one just like 3 days ago. I haven't updated it, but it's also based on Willow here. Microsoft is trying to use a new phase of Matter to build quantum computers. There's a $1 billion deal that we signed with Qatar, illustrating kind of the magnitude of some of these projects. And then we're already starting to look at genomics research with the Sanger Institute. So we're already starting to look to real world applications of quantum. So to explain what quantum computing is and why it's so amazing, I want to go back 200 years. On the left, this is the very first computer. It was built by Charles Babbage in Cambridge, England, and it looks like an old-fashioned typewriter to us. Even though it looks kind of old-fashioned, it actually is conceptually identical to the computer that we have today. This is actually the laptop I'm running the presentation on here on the right. Um, it has input devices and output devices, and in particular, all computers use switches. And of course, on the left, they were mechanical switches, but they're either on or they're off. Today we use transistors, but they're still the same basic idea. They're on or they're off. They're just smaller and faster. Quantum represents the first advance in how we build computers and how we do calculations ever in human history. And so that's something I want to communicate. Um, what is wrong with classical computers, with the computers that we're used to using? So to illustrate this, let's imagine first my favorite molecule. This is caffeine. It's not even a very large molecule. It only has 24 atoms. We've known for about 100 years what the equations are to simulate this molecule. So we have some equations, and we know what they are. If we could solve these equations, we would know every property of this molecule. We would know how it behaves exactly. And so in principle, we could do this. We could build a computer to solve those equations, but it would be a big computer. It would be like the size of the planet. So in principle, we could do it. It's just not very practical. Now imagine a larger molecule like penicillin. Again, we know exactly what the equations are, but now solving those equations would require a very, very big computer, actually the size of the observable universe. So even in principle, we will never be able to do this sort of thing. And the molecules that are interesting, like from a pharmaceutical point of view, are much, much larger, like tens of thousands of atoms. And so I just want to illustrate there's a lot of problems that normal computers could never even hope to solve. So it wasn't until the early 80s when this guy here, Richard Feynman, he had this idea. He was kind of thinking about these types of problems, and he realized that normal computers would never solve these problems. Why don't we try to look to nature for inspiration? Because nature uses quantum physics when it does these calculations. Maybe we could try to mimic this. And so he kind of suggested we do this. Back in the early 80s, no one knew how to do this. That was like Star Trek type technology. But it was a good idea, and people started working on this. And so for about 30 years, there was progress. It wasn't until around 2012, 2013 that people figured out how to build just one or two qubits. So that's like a quantum transistor. So let me first explain what makes it quantum. What is the fundamental difference about this? The fundamental difference is that a normal computer can only do one thing at a time. So imagine if you're trying to solve a maze, it has to try every possible solution for the maze, and this can take an impossibly long time. A quantum computer, however, there you see in the animation, it actually considers all the solutions simultaneously, and then the correct answer emerges. And how that works, I'll explain in a moment. I know that seems kind of magical, but but that's the fundamental difference, is that it's a completely different way to approaching the problem, and that's how it solves some problems much, much easier. Now, the way that it does this is that it does not use transistors. So transistors, remember, are either on or off, so we call them bits. It's a one or a zero. Quantum computer is something called a qubit, or a quantum bit. And qubits have these two special properties from quantum physics. The first property is something called superposition. And so superposition means that this qubit can be both 0 and 1 at the same time. Until you measure it, until you observe it, it's in this weird quantum state that we call superposition. The second property is something called entanglement, which says that this qubit over here can be correlated or entangled over here. And you may not know what this qubit is, but whatever it is, it will be correlated with this one over here. And Einstein called this spooky action at a distance, because we still don't understand why this is. We understand mathematically that this is the case, but I can't give you any cute metaphor for why this is. That's just how nature kind of built the universe. And so when we combine these two ideas of superposition and entanglement, it means that these qubits can represent many different configurations or solutions to whatever problem that we're considering. How do you do this? So the obvious question is, how do you build a qubit? Now that I've kind of explained why we want to build these qubits, there's actually many different ways to build a qubit. So there's many technologies to build a quantum computer. So the first technology, and you've probably seen this more than the others, is something called superconducting technology. And it looks like this golden chandelier that you might have seen here. This is an approach used by IBM and Google and a few others. I want to emphasize each of these technologies has advantages and disadvantages. There's no one perfect technology. And I'll say a few words about that next. So a second approach is something called ion trap technology. And in here, so this is actually the approach that we at Quantinuum use. The approach here is that every qubit is an ion or a charged atom, and we're physically moving them around, and then we use lasers to change the value. So we change the superposition and entanglement using these lasers. A third approach, which is kind of similar to ion trap, is something called cold atom, in which the qubits are kept in place using lasers. They don't physically move around, but they use lasers to keep them in place and then also to change the value of superposition and entanglement. And the fourth kind of mainstream technology is something called photonic. And here the qubits are made up of light particles called photons. And so each of these, again, has advantages and disadvantages. Um, right now, I would say the ion trap technology is the most promising. But the truth is there are probably going to be several winners, depending on the type of problem that you might do. So to say a little more about ion trap technology, so that glowing dot, that's an ion, a charged atom there. So we're physically moving it around, and then we're using lasers to change the value, the superposition and entanglement. The interesting thing happens is that when you get many of them, many qubits doing that, and then you entangle them. So remember when we put two of them together, we zap them together, it's the entanglement. So a quantum program is something like this. You have many qubits kind of choreographed working together to solve the problem. And so this is what a quantum computer looks like when you're running a program. I gave that example of chemistry, but the truth is that there's many areas of science and technology that will benefit from this. This is kind of a brief snapshot. Today, I only have a few minutes, and so I'm going to focus on the things which I think are most immediate and most relevant to you. But there really won't be any area of science and technology that won't be affected by quantum computing. To go back to that chemistry example that I mentioned a few minutes ago, so I've explained why this type of problem would be impossible on a normal computer. On a quantum computer, we only need a few hundred qubits to solve these problems. And this actually might be feasible in the next few years. And so again, quantum computers aren't just faster, they're completely different, and we expect that they will be able to solve problems which would have been completely impossible on any other computer. So that's why we're so excited about this. So let me give one example, one real world example. Um, I was horrified to learn that drug development is very inefficient. There's actually a 99.9% failure rate when a pharmaceutical company is trying to evaluate a drug. And that's because in the early phases in discovery and development, they basically just guess at what a drug, a molecule might do. They have to go through these different stages. They involve clinical trials, and this is very expensive. It actually takes, on average, about 10 years and $1 billion to bring one drug to market. And so this is bad at every level. It's time consuming, it's expensive, and it's risky for the people in the trials. And the best that they could hope for is that a drug will help most people and is not too harmful for most people. The side effects aren't too bad. With quantum, what we expect is something like this. We have a database of different molecules. We use quantum computers doing their simulations to figure out how that molecule will behave. We store that information, and then we use AI and quantum AI to take all this information and figure out the best possible drug. And then so it goes through this loop. Ideally, what we could even do is personalized medicine. So not just developing a drug for a whole group of people, but actually just for one individual or a small group. And that would really be impossible for a normal computer to do. And so I actually think this is going to be the most lucrative and also the most impactful for society, impact from quantum computing. What is funny is right now the most valuable chemistry problem, it's not pharmaceuticals, it's actually fertilizer. And the reason for this is because we've known for about 150 years how to make fertilizer, but we're very bad at it. It's called the Haber-Bosch process. It's very energy consuming and it's bad for the environment. We have noticed that bacteria are much better doing this than we are. We just don't know exactly how they do it. It has something to do with this molecule that I'm showing right here, nitrogenase, this enzyme. So what we would like to do is we would like to use a quantum computer to figure out how this bacteria, how the chemical reaction works for generating fertilizer, and then we could mimic it. And about 2% of the world's energy supply right now goes into just this problem. So if we could make progress, that would have a huge benefit, and be better for everyone. And so I just want to illustrate kind of the magnitude of some of these problems that we're thinking about. Another application is in the financial world. They obviously use a lot of numerical tools when they do trading and such. So a lot of times they're trying to anticipate what the stock market will do so that they can place their bets accordingly. The mathematics underpinning this is something called a Monte Carlo simulation. And so I've kind of shown illustrations. You do many simulations simulating possible outcomes of what a stock market might do. And then you try to kind of figure out the expected value of an individual stock. The more simulations you do, the more accurate the result. Unfortunately, using classical computers, there's sort of diminishing returns. You get a more accurate result, but not at a very fast scale. It turns out there's a quantum Monte Carlo algorithm, which is quadratically faster than normal computing. I apologize if you hear the siren in the background. I live in New York City, and there's an ambulance going by. Um, so what a lot of financial groups are doing is that they want to use quantum Monte Carlo to get more efficient convergent results faster. And so there's already a lot of interest, especially from JP Morgan and Wells Fargo. They're already built up a lot of groups like that. Another application is something called superconducting technology. This is related to that earlier graph I showed how some groups are using superconducting to build quantum computers. So let me say a few words about what superconductivity is. So when electricity goes through a wire, so right now, if you look at that image on the lower left, so the red dot is an electron. It's often bouncing in to the metal atoms there, those blue ones, and it wastes a lot of energy when it goes through. We've known for some time now that some materials, when you get them very, very cold, yeah, so right there, that's kind of a waste of energy if it goes through. Some materials, when you get them very cold, illustrated there, conduct electricity perfectly. There's no wasted energy whatsoever. And this is great because you can conduct more electricity through it and you're not wasting anything. What we would like to do is use a quantum computer to simulate this process and understand it better so that we could build better superconducting materials and ideally have this happen even at higher temperatures. And if we could do that, there would be so many advances in technology. So just to give one example, MRI machines, they have a lot of current going through there. They have to generate a very strong magnetic field. If you could make the magnetic field stronger, you can get higher resolution, which means, say, if you were trying to screen for cancer, you could detect the cancer earlier. And so I've given a few real world examples there, but this is the type of thing that we think quantum computing could help with. Even in the next few years, we could make some progress in this. Other examples are like battery technology, fuel cells, things like that. We're already starting to work with groups like BMW and Airbus on technology like this. I couldn't be giving this presentation without saying something about AI. There's been extraordinary progress the past few years. I'm sure several of you have been following this, but most people are only aware of about half the story because quantum will play an absolutely essential part in this. AI is amazing, but it can only predict what it can calculate. And as I've just tried to explain, normal computers can only calculate a limited amount of things. And so there's a limit of what normal AI could do. We're already aware of this. We've already started to integrate quantum with AI. And as a first step, NVIDIA has already partnered with several quantum companies, including us, and they've actually already set up a quantum research center in Boston. And the first partners are Harvard, MIT, and us. And so you probably know NVIDIA makes something called a GPU, or a graphics processing unit. So GPUs are still made of transistors. They're still normal computers in that sense. It's just that they're designed so that one type of calculation is very, very fast. And this type of calculation was originally conceived only in the context of graphics. So we're already starting to work together with NVIDIA on certain problems. So one example is generative quantum AI, when you're using AI to inform which quantum data that you will manufacture. You do some calculations on that, and then you again loop it through AI. And so they work together. So we're already starting to work on these types of problems. One example of this type of problem is something called an LLM, which I'm sure many of you have heard of. The more academic term for this is natural language processing. And we actually have a whole group based in Oxford just to understand this. So there's a whole mathematical theory behind NLP and LLMs, how these words are put together to make sentences and meaning and such. And it turns out that quantum NLP and LLMs, there's a lot more nuance and subtlety that it allows for because it's not strictly ones or zeros. And so we expect in a few years, not tomorrow, but in a few years, that there will be quantum versions of ChatGPT and OpenAI and all of these things. And so start looking for that. One thing that we are already starting to consider is a more general description of LLMs. Usually when people talk about this, it's in the context of human languages, and that could be English or Spanish or Chinese, but usually people assume it's a human language. That doesn't have to be the case. There's lots of languages which are not human languages. So for example, there's music. You could consider notes to be characters on an alphabet. You could consider base pairs in a genetic sequence as characters in an alphabet, and so forth. And so with that second example, we're already working with Amgen to look at genetic sequences as characters and then words and sentences and such. Um, and we've already obtained results which are at least as good as what they had obtained before. And so again, we're already starting to look at these very real world examples using quantum computing. I bet many of you have seen headlines about quantum computing and hacking. This tends to get the most attention. Um, so there is a reason for that, and I'll tell you the story now. So, in 1996, again, remember there were no quantum computers back then, but people had at least thought of quantum computers. This very smart guy named Peter Shor, he was considering this and kind of on his own in secret. There's a picture of him. He worked out what was one of the first quantum algorithms. So he wrote down the recipe for how a quantum computer could do hacking. And it was based on the ability of a quantum computer to factor numbers very efficiently, which underscores a lot of encryption. And it was actually such an efficient algorithm, it was exponentially better than what a normal computer could do. And so academically, it was interesting, but no one took it very seriously because, again, there were no quantum computers. And so it wasn't really any sort of serious threat, even though this represented about 99% of encryption on the internet. People are very scared now because quantum computers have become quite powerful in the past few years. This does represent a threat. In fact, it's people will have different opinions, but it may be possible in as soon as 5 years that quantum computers could hack most of encryption on the internet. Now, fortunately, people have been aware of this for a few years, and so they've already started to think about protections against that. And so people have developed new types of encryption based on mathematical formulas which quantum can't hack. And it was only about a year ago that kind of the results of this contest that was conducted were announced. So those images that I'm showing, those are actual images of what are called post-quantum encryption. So those are some of these new types of formulas that quantum can't hack. So there's three winners. So we feel pretty confident now that quantum cannot hack these. And so companies are already starting to integrate this into their cybersecurity. And I've given a few examples here. Ones that I'm aware of are Google, Apple, Zoom, Signal, Cloudflare, and Thales. I'm sure there's many others. These are just a few examples that I've noticed. Um, if you are in a position to do something about your group's cybersecurity, please don't wait until you read headlines about quantum hacking to do something about it. Please upgrade now. And the reason for this is explained in this picture called Mosca's inequality. It takes time to upgrade. And so think about not just how much time it makes to make that transition, think about how much time that you wish the data to be secure. And so when you compare that against the time that it would take for computers to actually breach this, You can decide whether you're in danger. So the 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 takeaway here is do something today to protect your data if you're in a position to do so. So that's how quantum computers can be used for hacking. I also want to spend a moment to talk about how quantum computers can be used to prevent hacking, because this seems to receive less attention. So it's also possible to transmit quantum data itself over long distances, and this is usually done over fiber optics or even with lasers. And there's several examples of each of these. The reason that people are doing this is because it's secure not just based on complicated formulas, it's secure based on the laws of physics. Because anytime that you observe a quantum state or you measure it, you're changing it, and that can be detected. And so to illustrate how this is, so imagine that you have this source of entangled qubits. So remember, entanglement means they're random, but they're random together. And you have the two people who want to communicate. Let's call them Alice and Bob. Alice measures her qubits in some direction, and Bob measures his qubits in some direction. And they do this like 1,000 times just for calibration. So they do this many times, and remember, because of this entanglement, if they're measuring in the same direction, they should always get the same answer 100% of the time. So they do this like 1,000 times, and then they compare notes. And if indeed that's the case for when they measure in the same direction, if indeed it matches 100% of the time, then good. It means the communication is secure, things are working correctly, they can go ahead and communicate for real. But now imagine there is some sort of eavesdropper. So the eavesdropper is intercepting a qubit, measuring it, and then replacing it. So they're trying to be sneaky about this. And if this were classical physics, this would be the perfect crime. In principle, there would be no way to detect that this had happened if the eavesdropper were really good at this. But remember, this is a quantum system. And so the fact that the eavesdropper has measured that second qubit, it means that they have changed the system and they can't replace that entanglement. And so now when Alice and Bob do this calibration check, and then they compare notes, some sizable fraction of the time, the results will be different. And they see this. There's mathematical evidence that something funny is going on. And so in this case, Alice and Bob know they should not communicate. And they just shut that down and try somewhere else. And so this is a very different type of protection from others, but it's very sturdy, and people are already starting to implement this. There's a lot of examples. I want to say just two brief words about cryptocurrency, because I'm asked about this a lot. No, you cannot use quantum computers to mine Bitcoin or other cryptocurrencies, but if the cryptocurrency is using the old type of encryption, you could use a quantum computer to hack it. And so all that encryption will need to be upgraded. The second thing that I'll say is that there's something called a quantum token. So this is like other tokens. It's kind of evidence that you own something, and it could be money or a blockchain or anything else. Decades ago, people imagined something called a quantum token, but it was impossible to build, even though it had all these advantages over classical. The technology wasn't good enough. We've actually already started to do this. About a year ago, we're actually starting to implement this already. And so this will be an essential part of any quantum internet or any quantum system. I next want to say a few words about measuring the progress, because it's difficult to keep up with all the headlines, even for someone like myself who's in the field. This was my favorite headline, the one with the weird machines. These are actual headlines that have happened the past year. And so I want to say a few words about how we measure the progress and how we objectively do this. And so to explain this, I want to first say something about quantum error correction, because this is really important. So all qubits, no matter how you build them, have some chance of error. They just won't do what you want them to do. And that's actually okay. We can correct that as long as the error rate is pretty small to begin with. This is actually an image from Google about a year ago. It actually shows the process of identifying errors and then correcting it on some of their machines. And so that's okay. So this process called quantum error correction, it basically involves just taking the information of one qubit and smearing it over several others. And so that's how we do this. So this is a chart showing those two issues. So there's the number of qubits, and obviously more is better because it allows you to consider more solutions to your problem. And then there's the error rate, or how, the fidelity of how good these qubits are. So we start life in the upper left-hand corner. We've started with a few um, qubits with a large error rate, and we want to get down to the lower right-hand side where we have many qubits of great quality, a very small error rate. So it's a question of how do you do that? Um, at this point, I would kind of ask people's guesses, but that's a little difficult to ask. So let me explain where at least two technologies are. So superconducting technology right now has about 1,000 qubits, which is actually quite impressive. Unfortunately, they haven't been able to bring the error rate down very much. The error rate is still kind of high. It really hasn't even surpassed the threshold, that dotted line there, of what you need in order to do quantum error correction. And so there's still kind of at that verge of being able to do that. Now, ion trap technology, which is what we use, we have fewer qubits. We have about 100, but the error rate is much, much less. And so viewing ahead towards that path, towards many quantum error corrected qubits, um, I know on this image it's a little tough to tell, but I think it's an easier path to get there from the ion trap technology. But again, I think there will actually be several winners in the years to come of different technologies of how to do that. Now, in terms of the performance, I'm sure many of you have heard of Moore's law. Over several decades, we've seen that normal computers have doubled in performance roughly every 18 months. Quantum is on a much faster trajectory. So I put Moore's law on that orange line. The red line shows this is the actual data from our machines over the past 5 years. Um, that's actually about a 10x increase every year. You notice the vertical axis is logarithmic. So those look like straight lines, but that's exponential progress. So quantum has been much, much faster. And that's why just a few years ago, you might have heard, oh, quantum is nowhere near as powerful as classical. Several years ago, that was true. Now we're actually starting to overtake classical for some specific problems. And so it's really amazing. Based on this trajectory, we expect practical applications within a year. So very, very soon, you will be start hearing about the first practical applications of quantum. So this is a study done by McKinsey Consulting. Every year they do a quantum computing report here. They're now estimating the value created from quantum to be in the trillions. And they even break it down into the different sectors, kind of estimating the value here. I personally think, and I mentioned this earlier, that pharmaceuticals will be number one. I think that will actually be the most valuable um, solution created from quantum computing, but at least for now, they have it in the financial industry. But again, there are so many different industries that will be affected by this. So whatever your industry is, please understand how quantum will fit in. In terms of investment, this kind of shows a chart here. You'll notice there was no private quantum computing sector until around 2012. And that was when these breakthroughs started. And so the first company started, the first investment came in. And since then, it's been on this upward climb. And just this year, it's already been in the billions. It's been more than $1 billion already this year. And so when they do this report next year for 2025, it will be way up here. So there's a lot of money and interest going into this. This just shows against the government. In terms of the global ecosystem, a lot of governments are getting into this. So the US is certainly supportive of this. Canada has a fantastic team, especially based in the Toronto area. China is very, 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 very invested in quantum, especially quantum communication. Um, that that idea of sending the qubits over fiber optics or over lasers. Um, and then different places in Germany, and so sorry, in Europe, most specifically in Germany, and so this really is a worldwide thing. It's going to be very interesting in the next few years how this shapes up um, in a global sense. So in terms of a timeline of what you can expect in the next few years, so this year, I believe, if not in the next 3 months, but at least in early 2026, you will start to see the first practical applications of quantum computing. Quantum hacking doesn't seem possible yet. Otherwise, I think we would have heard about it already. But in 5 years, I think we'll not just have applications. I think they'll be pretty amazing. There'll be things that we really couldn't have come up with before. And it is possible that we could start to see hacking from quantum computers. In 10 years, by 2035, I think it will be so integrated into technology, we couldn't even imagine things without it. And the applications will seem almost miraculous. And hacking from quantum will be almost inevitable. So again, I urge you to upgrade. What you can do now, whatever your industry is, start a quantum readiness team. So just understand more about quantum and how it's going to affect your industry. Do some sort of project, work with a quantum computing company. It doesn't have to cost you millions of dollars, but do something just to kind of understand what it is and how quantum will affect your industry and become familiar with this. And then again, upgrade your encryption to post-quantum encryption. And so that's, oh yeah, one final thing. If you'd like more information, these are the kind of two things that I look to for information. So the first is it's a website called the Quantum Insider, and it's a great source of all the latest news, the technology and the business side of things. And so I've given the URL there. And then that report that I just showed you a moment ago, it's available for free, and that's the short URL. If you'd like to take a screenshot here, you can look at that yourself, and it's a great report and goes into quite some detail. So that is it for my slides. If you have any further questions, please feel free to email me. And this is my LinkedIn QR code here if you'd like to stay in touch and such. And so with that, I'm happy to answer any questions that people might have.